So, we have put together all the machinery to describe the interacting theory of electrons and photons, and there are quite simple rules which can summarize everything, and they are actually heavily used in doing the calculations. They were invented by Feynman, so obviously they carry his name, and what they allowed us to do is to quickly write down the amplitude for a given process, and this process will be represented by Feynman diagrams, which are nothing but a space time picture of what is going on. Now, while doing this, we quickly forget about all the quantum dynamics in the sense of having wave functions and distributions, etc. We will just look at the whole thing as in a particle language, some particle going from one place to another and interacting with some object and then scattering from it, etc., and so on and so forth. And we have seen two different descriptions for this. First, for the electrons, we have written down the element of the scattering matrix as the part where nothing happens, and then a part where the electron wave function responds to the electromagnetic field represented by A slash in this process. Now, the electromagnetic field can in turn arise from a distribution of charges and currents, and we had that relation as well, which was summarized by this equation. So, putting those two things together, we can quickly iterate the procedure that electron responds to photon, and photon is a consequence of electromagnetic charges distributed in a particular way as well as their movements. And so, the net result can be written in a simpler form, where now we have only various combinations appearing in terms of the wave functions of one type or the other. So, this quantity in the bracket is nothing but what was there in the electron equation, but the A part is now written explicitly in terms of the source and this is a combined equation which is in a form which can be iterated as many times as necessary. So, if the photon is an external field, well, we do not write it in terms of its sources, but if it is produced by another electron, then it can be written by J mu. J mu again is represented by psi bar gamma mu psi of some other source, which in turn may have been interacting with its own electromagnetic field, and one can just iterate this procedure as many times as you want to produce the necessary description which goes along with a space time picture provided by Feynman diagram. This equation, as I have written, is formally exact because what appears on the right hand side is psi tilde, which is the exact solutions of the Green's problem. When trying to use perturbation theory, we start out with the simplest answer where psi tilde is replaced by the initial plane wave distribution. You get the result from this equation, then iterate it. Next time you put in the answer inside it, which was found at the first order. And that gives rise to all the description which we can now easily summarize in terms of this so called Feynman rules. So, we now have a procedure to is to first draw all the diagrams So, first we draw the diagram to any desired order and then convert what is represented by this diagram to algebraic expressions. And clearly in doing this perturbation theory, the parameter of which powers are counted is the charge E, and you want to calculate any object say to the first order in E or second order in E or third order in E, it can be easily done by just expanding psi tilde and J mu iteratively one step after the other and constructing all possible descriptions of the processes. So, the rules can be easily obtained for the tree diagrams, where the tree diagram refer to a topology of this space time picture. There are no closed loops, and once one learns how to go beyond that, that requires some knowledge of quantum field theory. And then we have loops, but we know how to handle the loops as well in the same picture, and might have to include a little bit extra stuff to deal with loops, but that is not too complicated. Once a complete field theory description is made, the tree level rules are easily extended to interactions of arbitrary type. So, what are these rules? One is, well, draw all the diagrams to desired order in E, and as we have constructed the whole thing, these are space time pictures. So, the rules as we have constructed will be obtained in the coordinate space. The second step is, there are various segments of these diagrams. So, they will be referred to as vertices. There are propagators, which can also be called internal lines and external lines, which corresponds to particles in the initial and final state, and the numbers of various things of various types is actually related, and for tree diagrams one can easily convince oneself that the number of vertices is equal to number of propagators plus 1, and that is easily obtained from the equation which I wrote down for the scattering matrix. Every time one expands the right hand side to a particular order, there is an extra factor of a propagator coming in, and there is an extra factor of the power of the charge E coming in. So, the power of E actually counts the number of vertices, and both of them at every order increase by 1. So, one has to only identify the lowest order term where there will be a single vertex, but no propagators, and that fixes this particular relation, and the power counting is just the factor which we have put in the equation minus I e gamma mu and an integral over the location of the vertex, that is because the vertex represents the interaction and interaction could have occurred anywhere in the whole space time. So, every vertex basically counts the power of E. So, if you want to calculate say to third order perturbation theory, the theory will or the diagrams will have 3 vertices inside them. There is no other place which contributes a power of E. So, that much is for the vertex. What about the propagators? We have seen both type of the propagators corresponding to the fermion or the photon, and so each propagator gives the factor I s f x minus y. This is for Dirac fermion or I d f x minus y together with this g mu nu if necessary to contract the indices for photon. So, this essentially counts the second part, that propagators each will bring in a certain weight, the vertices bring in a certain weight, and the last weight will be the external legs which will have a corresponding each factors line gives the so called wave function factor, and this can be of different type depending on what the particle is. If it can be u for an electron in the initial state or a v for a positron, it can be u bar for a electron in the final state, similarly v bar for a positron, and if it is a photon, we have seen that the description is given by this polarization tensor epsilon mu. So, this now has completed the description of the diagram. Every vertex, every propagator and every external line have been accounted for, and beyond this now there are a couple of factors of the signs which appear. They have to do with our conventions as well as the statistics which has to be followed by the theory, and this may not be too obvious, but once one works out the full field theoretical formulation, it becomes quite straightforward to handle. So, there are signs and there are two sources of this particular sign. One is that for positrons in initial state, there is the sign is minus 1 raised to the power of the number of positron, and this arises from the various rules we have used to define the wave functions for the free Dirac particles, and in particular there was an epsilon r which defined the sign of the energy of the solution, whether it was positive or negative. For positrons, epsilon r is equal to minus 1, and which enters in this whole analysis in some particular way. So, that is one overall sign, and for every closed fermion loop and for each exchange of external identical fermion lines, there is a factor of minus 1, and this is a consequence of statistics. In dealing with the single particle theory, we have not seen statistics directly, but in a field theory it has to be properly included, and for the fermions, the anti-commutators between various fields, they produce this statistical sign of minus 1 when two of them are exchanged, and the closed fermion loop is related to this statistical sign, as I have illustrated in analysis of the Lorentz group, that it is something which can be visualized as a rotation by 2 pi, and that rotation by 2 pi produces the same sign as the sign for the statistics. So, these are overall signs picked by the various conventions which we have used. And one more thing one can keep in mind, that the overall sign can be convention dependent, because quantum wave functions cannot be specified with an absolute value of phase, but the relative signs they have to be fixed correctly, because they correspond to observable interference effect, and if you do not get it right, the answer will not be correct. So, this is the summary of how to convert a given Feynman diagram to a algebraic expression describing the scattering amplitude, and we will work out various examples of different level of complexity to illustrate these rules and algebraic calculations, but there are some more things which can be easily added to these descriptions, and in practical calculations these rules are often used in momentum space, and which means that we will Fourier transform everything from the coordinate description to momentum space, and that gives rise to a description which is actually simpler, and the reason for it that the propagators which we have written down look much simpler in momentum space than they look in position space. And what happens in this Fourier transform is that you have generic factors like e raised to I p dot x for every point. So, in case of vertex it is just a single factor. In case of a propagator it will be a factor like e raised to I p dot x minus y, where x and y are the two ends, and then one has a description of the vertex and propagator both in momentum space. And then one can combine this various factors of e raised to I p dot x, which accumulate at every vertex from the position of the vertex itself, as well as all the propagator as well as external lines that may be connected to a vertex, and one has to do a integral over the position of the vertex, which can be now easily done in a rather trivial fashion. So, at every vertex factors of type e raised to I p dot x accumulate and then integral over position of the vertex, which I wrote down, produces a delta function. Because integral of factors of e raised to I p dot x will just produce delta of the summation of all the momenta corresponding to that particular and you can see that as delta 4 summation over all the momenta, and it have to be counted in terms of the direction described by the arrow of the various lines. And so, one has to now keep track of the momenta, but in a direction dependent manner. So, now we have a the momentum space diagram will have momentum with direction, which is represented by drawing an arrow on the line for every line, and extra momenta So, one draws a generic diagram. We have seen that the number of vertex is 1 plus the number of propagators. So, the external lines have a incoming momentum, which is provided by the definition of the problem. We can't do anything with it, but all the internal propagators will have their own momentum. Then we will impose all the constraints at every vertex that will keep on eliminating all the internal momenta one by one, and what happens is one gets the number of delta functions correspondingly equal to the number of vertices. Now, this number of delta functions are capable of eliminating all the internal propagator momenta for the tree diagrams, because the number of vertices is 1 plus the number of propagators, but that extra 1 means that there is an one overall delta function is left. So, that has to have a meaning, and it is quite obvious what that meaning is. For tree diagrams, all interline momenta are uniquely assigned, because this relation, which I can schematically just write, that V is equal to P plus 1 and an overall delta function for the momentum conservation remains, and that is the total outgoing momentum must equal total incoming momentum for all the external legs of the diagram. If that is not satisfied, then there is no interaction at all, because the theory has a overall translational symmetry and the total momentum conservation must hold. So, this one overall delta function completely factors out of the whole problem. We did the counting for tree diagrams here, but it is true as well for any arbitrary diagram. It may have extra loops as well, but this overall momentum conservation is still valid. So, there will always be a factor of delta 4 P f minus P I, and many times it is convenient to factor it out of the whole calculation as well, and write only the remaining part of the object which corresponds to the so called transition matrix element. So, in case of diagrams with loops, there remain undetermined momenta going around, which are not at all constrained by what the external legs provide, without running into any conflict with momentum conservation, and this have to be integrated over, because the Fourier transform always produces integrals d for x or d for p. If something is not eliminated by delta functions, well, you have to perform that particular integral, and in case of loop diagrams, these integrals may have to be handled with little care, because their momenta go from minus infinity to plus infinity, and these integrals have to be often handled with care. We have not seen anything like the loop diagram picture so far, but when it occurs and we will see some examples, you have to be careful in how you deal with these integrals over momenta. And typically each loop gives a structure which is of integral in 4 dimensions, and the care is required because some of these may diverge and so the care which I mentioned is a procedure which is called regularization. So, one has to do a little bit of jugglery to take care of these loops, but that is a necessary price to pay once you go beyond the simple equation of motion to a field theoretical language. And the normalizations of photons and electrons I already wrote down, but I will repeat them once again. So, the normalization of external lines are chosen as per the plane wave convention. In case of fermions, it is a structure which is of the form square root of m over E, which normalizes according to the Lorentz contraction factor. V is just the box normalization for unit volume, and the spinor is u or v depending on the positive or negative energy solution. And for the photon, we have written formula which I will repeat. It is 2 k v epsilon mu, giving the polarization tensor, and then the two forms either the positive energy part or the negative energy part. So, this is a sort of complete description, quite elaborate in terms of various conventions, but it is sufficient to now do calculation to any desired degree in the perturbation expansion for any process described by the scattering matrix. I would like to make a few comments about the nature of we will get a series working out terms one by one in the analysis, but then we want to compare it with other kind of perturbative expansions which we have seen in either in mathematical physics or in non-relativistic quantum mechanics, and compare what are the new features or related features which appear here. So, one fact here is that the expansion contains denominators of type p square minus m square plus I epsilon. Generically, this is the feature in relativistic theories. For massless photon, m is 0, and for fermions it can be mass non-zero, but these are the factors which appear, and they vanish in states which are called on shell, which obey the dispersion relation exactly, means p square equal to m square. In the expansion which we are constructing in the virtual quantum states, these are so called off shell propagators appearing as internal lines, they do not vanish, and this is related to the fact that all these internal states are transients, they are not asymptotic states, they can live for short times, and in the short times we are allowed to have fluctuations in energy as well as momenta consistent with the uncertainty principle, and so the p square and m square can go a little bit away from each other's values, and the denominators then do not become 0, and that is a part which actually contributes to physics. And what we do in this quantum theory is calculate the contribution coming from all these internal virtual states, and they add up to giving us a full result for the perturbation theory. And one can see the relation of this kind of objects to the description which appears in non-relativistic theory, where in non-relativistic quantum mechanics, there are so called energy denominators in perturbative expansions, and they correspond to virtual states which live for very short time. So, one has a transition from one state to another, and then you come back to the original states or produce another transition to another state, and so on and so forth. And the momentum is explicitly conserved in the non-relativistic expansion, but energy is not, and that uncertainty in energy allows us to deal with this energy denominators which appear in the expansion, and there. So, the P is conserved while E is not. Here the in the relativistic case, we have already conserved the momentum at every vertex. It came out from our formulation automatically, but the uncertainty is appearing as the dispersion relation between energy and momentum is not conserved for all these internal lines. So, it just got disguised in a different form, but the uncertainty principle is having a particular effect in the structure of the calculation and how we then sum over all these internal diagrams. And one can see the relation between the two by just a simple decomposition. If different time orderings of are separated, we did the reverse in combining the step functions into a single description with I epsilon prescription and so on. But if we now go back and rewrite this propagator as sum over two different poles, one corresponding to positive energy and one corresponding to negative energy, then all this factor of p square minus they separate out into the energy denominator of the same nature as seen in non-relativistic quantum mechanics, and in that case E is not conserved for individual terms. Of course, the total energy momentum conservation is still exact, that corresponds to the overall delta function of P f minus P I. All this stuff is the internal virtual states which do not have to obey this rule, and that is exactly the place through which the quantum effects are entering. If we do not allow this fluctuations of the states to off-shell part, then we will have only the classical mechanics and no quantum effects at all. Okay, so, this is one particular feature for the organization of perturbative expansion, just illustrating what it is. The other feature which is useful to note is the nature of this particular series in terms of its convergence, that you can write down order by order terms in E, but can we sum up these things in any meaningful fashion? If not analytically, then can you do it numerically? So, that question has a unusual answer, that the series is actually not convergent, and so we have to put in some effort to make some sense out of this particular series. So, the first thing to note that the series expansion is in powers of the electromagnetic charge, but if we go to processes which are charge conjugation symmetric, then one can change E to minus E and expect not to see any difference at all in the result, and so the series expansion is in powers of the fine structure constant, and which in the normalization which I have been using, it is equal to E square by 4 pi, and so E goes to minus E, alpha does not change, and that is a natural parameter which appears because lots of processes which we calculate in this description are charge conjugation symmetric. And now one can ask, what is the convergence property can then be analyzed in the complex alpha plane around the expansion point alpha equal to 0. This is a standard machinery of mathematical function when expanded in a series, whether the series has a analytical form and it can be summed to any particular order, or it is non-analytical and then it has no meaning in terms of a expansion, and the result is that the series is not convergent for any alpha, which means more explicitly the expansion has 0 radius of convergence. But it has another name, which is that the series is asymptotic. And we have to understand these features in a little bit of detail, why it is so, but a quick answer is that the theory is unstable when analytically continued to alpha less than 0, and there is the whole branch cut. For the whole negative real axis of alpha, and we will see the argument which substantiates this result next time. It was provided by Dyson.